Alright, everyone. So today I'm going to start a new series on tensors. And the reason why I'm choosing the topic of tensors specifically is because for my senior year, I started writing an introductory text on tensors as part of an independent study. So I'm going to share some of the content that I have written and present it in lecture format. So we begin with vector spaces. Now, I recently released a video on my main channel on the same topic, but this will cover a little bit more, and it will assume that you already kind of know what a vector space is. So this is supposed to be sort of a review. So we begin with operations, as I did in the other vector space video. So if we have an operation of addition, that assigns, if we have two elements u and v in some set v, then addition assigns those two elements an element u plus v, which is also in v. So you can think of it as a function from the Cartesian product of v with itself to v. Of course, we also have scalar multiplication, where if we take some element v in a set v, and then we have an element lambda in a field f, then those two elements together are mapped to an element lambda times v in the set v. So you can think of it as a function from v cross f to v. So sometimes there are other operations on a vector space. You can sometimes have an inner product. There's also sometimes a cross product, and there can be other operations. But the point is, these two are the only required operations for a vector space. So now let's define a vector space proper. Vector space. So a vector space is a set V with two operations, addition and scalar multiplication, which satisfy the following properties. So we have commutativity, so u plus v equals v plus u for all u and v in v. We also have associativity, and this gives us u plus v plus w equals u plus v plus w, and lambda times mu times v equals lambda times mu times v for all u, v, and w in v, and for all lambda and mu in the field. So we also have distributivity. So we have that lambda times u plus v equals lambda u plus lambda v, and lambda plus mu times v equals lambda times v plus mu times v for all lambda mu in f, and for all u and v in v. There also exist certain identities. We have an additive identity, so there exists some element 0 in V such that u plus 0 equals u for all u in V. And there also exists an element 1 in the field such that 1 times u equals u for all u in V. So, and the final property we have is that of the additive inverse. So, for all u in V, there exists a V in V such that u plus V equals 0. So every element has an additive inverse. These are the 5 core properties of a vector space. And notice that the field carries importance. We say that vector space V is over a field F. And if the field equals the set of real numbers, then the vector space is called a real vector space. And if the field equals a set of complex numbers, then that is called a complex vector space. It's also important to know that a vector is an element of a vector space. So now we'll be going over a couple theorems. These are the same theorems that I proved in the other vector space video on my other channel. And they're pretty straightforward, so I'll go through these really quickly. So first theorem, a vector space has a unique additive identity. So suppose that A and B are both additive identities. Then it follows that A equals A plus B because B is an additive identity. And by commutativity, we have that it's equal to B plus A. And since A is an additive identity, that simply equals B. Therefore, A equals B, and so the additive identities must be the same. So therefore, the vector space has a unique additive identity. The second theorem is that every element in a vector space has a unique additive inverse. So suppose that for some vector v, then u and w in v are both additive inverses of v. We have that u equals u plus 0, which, since w is an additive inverse of v, is equal to u plus v plus w. By the associative property, we have that this is equal to u plus v plus w. Because u is an additive inverse of v, u plus v is equal to 0. So we have 0 plus w, and therefore u equals w. So there must be only one unique additive inverse. All right, the next theorem, 0 times v equals 0 for all v in the vector space. Again, the proof is fairly simple. 0 times v equals 0 plus 0 times v. This is we're using field properties here, and by distributivity, 0v plus 0v. And then if we subtract 0v, or if we take the inverse of 0v and add it to both sides, we get 0 equals 0 times v. And that's our desired expression. So our next theorem is that a scalar times the 0 vector is equal to the 0 vector. So a times 0 equals 0 for all a in the field. The proof is very similar to the one we had before. So if we consider a times 0, that equals a times 0 plus 0 by property of the additive identity. And that equals a times 0 plus a times 0 by the distributive property. So if we take the inverse of a times 0 and add it to both sides of the equation, we get 0 equals a times 0, which is our desired result. Finally, the last theorem that I'll be covering is, or the last theorem I'll be covering for now, is that negative 1 times v is the additive inverse of v. So this is the additive inverse of v. So we want to prove that v plus negative 1 times v equals 0. So here's how we do that. Let's consider v plus negative 1 times v. That equals 1 times v plus negative 1 times v. And then by, I guess, the reverse distributive property, 1 plus negative 1 times v. And that equals 0 times v, which, as we previously established, is equal to 0. Therefore, v plus negative 1 times v equals 0, so negative 1 times v is an additive inverse of v. So that's basically all the content from the first other vector space video that I recorded. This is more fast-paced. This is supposed to be a review, as I mentioned, but there are a couple other things that we should know when studying tensors. So first, let's talk about subspaces. So a subspace of a vector space is a vector space that is a subset of another vector space. It must be a vector space under the same operations defined on its superset. So basically, if you think about, like, let's draw this. Let's say R3 is our vector space. An example of a subspace could be like a sort of maybe a plane passing through the origin. And the reason why is because you can verify that all the properties of vectors on this plane, they're a vector space under the same operations as in R3. So maybe we have some arrows here and here. We can define addition on it as well, and then we can define scalar multiplication. And the punchline of this, and the way you can prove that a vector space is a subspace of another vector space is the following remark. So if we have a subspace W and vectors V and W in W, we must always have that V plus W is in W and lambda V is in W for all lambda in the field. And we're considering that W is a subset of some vector space V over a field F. So that's a bit about subspaces. Let's talk about a little bit about some other aspects of linear algebra. So we have something called a linear combination. And if we have a linear combination of some vectors u, v, w, etc. in V, it's simply an expression a times u plus b times v plus c times w plus dot dot dot, where a, b, and c are scalars in a field. So we have that subspace W where V and W is in W and lambda mu is in F must contain all linear combinations lambda V plus mu times W. So in my text, I leave this as an exercise for the reader, but I think this is easy enough that I can just prove it right here and now. So we know from our previous remark that lambda V must be in W for all lambda in F. Similarly, we must have that mu times W must be in subspace W for all mu in F. Now note that both lambda V and mu W are in W. Therefore, the addition of those two vectors must also be, the sum of those two vectors must also be in W as well. So we have lambda V plus mu times W must be in W for all lambda mu in F and for all V W in W. Hence, the theorem is proven. So now let's turn our attention a little bit toward matrices and some related topics. So let's talk about a column space. So if we have a matrix A, the column space contains all linear combinations of the columns of A. So let's say we have a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. The column space would be the set of all lambda times 1, 4, 7 plus mu times 2, 5, 8 plus, I don't know what comes after mu, nu times 3, 6, 9. So for all lambda mu nu in F. So yeah, that's the column space. So furthermore, let's talk about linear independence. So we say that a set of vectors v1 to vn in V, we call them linearly independent if we have a linear combination of them that equals 0, that must imply that the coefficients are all equal to 0. So if you have a linear combination that equals 0, and the only way that the linear combination can equal 0 is if all the coefficients are 0, then those vectors are linearly independent. So what does that mean geometrically? Well, let's say we have R2, and maybe we have vectors like so. Is there a way to combine them in such a way that they equal, that the sum of that the linear combination equals the 0 vector? And the answer is no. Well, the only answer is that the coefficients have to be 0. So let's call this V and let's call this W. We must have that if we have AV plus BW equals 0, then A equals B equals 0. But let's say we have vectors U, V, and W. Well, if we think about it, or maybe let's do that. Let's say we have 2 times U, so 2U, and then 2V, and then minus W, so I'm not sure if you can kind of see, it's sort of transparent, but this gives us 2U plus 2V minus W equals 0. And note that these coefficients are not equal to 0. They're not all equal to 0. Therefore, UVW is not linearly independent. Alright, so let's talk about span. So we say that a set of vectors v1 to vn spans a vector space V if any vector in V can be represented as a linear combination of v1 to vn. So let's go to another theorem. So let's say we have a system AX equals B, where A is a matrix, X and B are vectors. The system is solvable if and only if B is in the column space of A. So, first, a bit of a remark. I'm going to go through the proof very quickly. I'm just going to assume that there's some familiarity with matrices. So, we say that we can say that the column space of A, is the set of all vectors AX, where A and X have appropriate dimensions. Because if you think about it, let's say we have A and then we have X, that's basically you can think about it like, and you can see this is clearly in the column space. So that's a very sort of rough outline of how I come to this conclusion. So more importantly, if B is not in the column space of A, then no linear combination of the columns of A will equal B. So no linear combo of columns will equal B. Therefore, X equals B must have no solution by our above remark. Therefore, AX equals B is solvable if B is in column space of A. Then, going the other way, if AX equals B is solvable, then by the above remark, there must exist some linear combination of the columns of A that equal B. And so B is in the column space of A. So we've proved it in both directions. Therefore, the system AX equals B is solvable if and only if B is in the column space of A. So a couple definitions before I'm done. So let's talk about a basis. So set V1, V2 to Vn form a basis if these vectors are linearly independent and they span V. An associated concept regarding the basis is the dimension, which is the number of vectors in a basis. Finally, we can describe a vector in terms of its components. So, if v1, v2, vn is a basis of V, then if U equals a1 v1 plus a2 v2 plus plus an vn, we can describe the vector U by its components a1, a2, an. So that's a little bit of a crash course on some of the rudiments of linear algebra. We will be needing some of these concepts as we go through the various concepts in tensors, tensor algebra, and tensor calculus. So hopefully this video was informative or at least a good review, and I'll see you in the next video.